Welcome to this explainer. Okay, if you've ever had to work with complex dynamic systems, and I'm talking about things like tuning a car's suspension or designing aerospace control loops, you know firsthand that they can be an absolute nightmare to solve. Today, we're going to tackle this by adopting a professional engineer's mindset to master an absolutely incredible mathematical tool, the Laplace transform. Think of it as our ultimate universal translator, taking our absolutely hardest problems and making them astonishingly simple to work with.
So let's just dive right into this stark contrast that really defines our whole problem here. On the left side, we've got the messy, real-world time domain. We represent this with a little t. This is where we usually describe dynamic systems using grueling, complex differential equations. Honestly, they're terrifying. But look on the right side. That is our destination, the frequency domain, represented by a little s. Over here in the frequency domain, those terrifying differential equations just magically become simple, straightforward algebra. It's literally a game changer. Our entire goal today is figuring out how to jump from that difficult left side over to the easy right side.
Since we're dealing with some dense math today, here's a quick roadmap for us. 1. The math translator. 2. The processing plant. 3. The transformation table. 4. Basic functions. And finally, 5. Initial conditions.
All right, kicking things off with Section 1, the math translator. Professional engineers rely on this as their ultimate mathematical translator. And the really crucial point is right here in this notation. See that big L? That stands for the Laplace transform. What we're actively doing here is taking a function of t, time, and translating it entirely into a brand new algebraic material, a function capital F of s, which is frequency. We are literally changing the language the math is speaking so we can actually solve the problem easily. And of course, the intention is to translate it back once we're done. Moving right along to Section 2, the integration processing plant. So to really look under the hood at how this translation is even possible, I want you to think of this formal integral definition as an engineering processing plant, right? Your time-based function, f of t, goes into the plant. Inside, it gets multiplied by our mathematical solvent, e to the negative st. Then, the plant just compresses it over all time, integrating from 0 all the way to infinity. And that integration process, it dissolves the t variable completely, leaving only our brand new frequency variable, s, behind. It's brilliant. Let's actually see this plant in action by solving an example step by step. So we input a simple constant function of 1 right into the plant. We integrate it against our solvent, e to the negative st. Next, we evaluate those limits as t approaches infinity. Now, because we assume s is strictly greater than 0, that upper limit term just goes right to 0. Subtract the lower limit, and out pops this beautifully simple result, 1 over s. Now, doing the exact same process for our next example, let's see what happens with an exponential function. We input e to the power of at t, we multiply it by our solvent, and we combine those exponents to get e to the negative t times the quantity s minus a. We process it through those exact same integration limits from 0 to infinity, and just like that, we arrive smoothly at a brand new algebraic expression, 1 over s minus a. Which brings us to Section 3, the engineer's transformation table. You know, a professional engineer rarely builds from scratch every single time, which is exactly why we rely on established standards. So welcome to your new best friend, Table 2.1. This is a massive relief, honestly, because it transitions us away from those tedious integration limits and takes us straight into rapid-fire algebraic substitution. We've mapped out the absolute most common inputs here, like constants, exponentials, sine waves, powers of t, directly to their algebraic outputs. If you can just identify the shape of your input, you literally just grab the answer from the table.
Okay, let's test it out in Section 4, transforming basic functions.
Let's put this incredible cheat sheet to work. This really brilliantly illustrates how fast we can move now. So, need to transform a constant 5? Just look at Rule 1, and it simply becomes 5 over s. What if you have e to the negative 3t? Easy. Using Rule 2, it becomes 1 over the quantity s plus 3. What about sine of 2t? Well, using Rule 3, that maps cleanly to 2 over s squared plus 4. Honestly, no integrals required. We can even handle far more complex dynamic elements. Looking at some more hits from our examples, t squared uses Rule 7 to become 2 factorial over s cubed, which simplifies to just 2 over s cubed. And for something crazy like t to the 5th times e to the 3t, we just use Rule 8, yielding 5 factorial over s minus 3 to the 6th power, or 120 over s minus 3 to the 6th. Even these dense problems collapse instantly into simple algebra using our standardized table rules. And finally, Section 5, handling initial conditions. This final step right here reveals exactly why Laplace is the absolute perfect tool for real-world dynamic systems. Take a really close look at formulas 10 and 11 from our table, which deals specifically with derivatives. When we transform a first derivative, f prime of t, we get s times f of s minus f of 0. And for a second derivative, it's s squared times f of s minus s times f of 0 minus f prime of 0. Notice how it elegantly just subtracts those zero terms right out of the gate?
Now, those aren't just random variables. Actually, f of 0 and f prime of 0 are your initial conditions. See, in the real world, dynamic systems always have starting points, like the initial velocity of a suspension system or the starting charge of a capacitor. This means the Laplace transform brilliantly bakes the initial starting state of your system directly into the algebra from the very first step. You don't have to go hunting for constants of integration later on, like you do in traditional calculus. It's all right there.
So, as we leave the grueling differential time domain behind us, think about your own engineering workflow. With your starting conditions perfectly baked into simple algebra, how much time and headache are you going to save on your next complex project now that you have this ultimate toolkit? Definitely keep that in mind the next time a differential equation tries to slow you down. Thanks so much for joining me on this explainer, and keep exploring.